So good afternoon, February 2nd, 2015. This is MATB110, section 1, calculus 1. Today is day number 9 in week number 5. So let's get started. First of all, welcome back to this class. Good afternoon. This is MATB110, calculus 1. Okay? If you look at the calendar, we've just gone through week number 4 last week, and you did your first quiz last week, and you have the second quiz this week. Okay? So do you remember what you need to do for the second quiz? Which sections in the textbook is concerned with the second quiz? This is coming Wednesday. 2.4, 3.1, and 3.2. Okay? So 3 different sections. In other words, you can expect 10 minutes per question, 3 simple questions. Okay? And you need to submit your third homework assignment and also submit a second grade homework assignment through the Moodle family this coming Wednesday and Thursday. Oh, yes. May I remind you something? I encounter the situations, and indeed I start to encounter situations that some of you turn in your homework late. Okay? Now, according to the policy of the class, no late homework will be accepted except for legitimate reasons by reported homework submission dates. Now, this is what I encountered last week. I was ending the class on Thursday, and one student came to me and said, "Oh, I'm sorry, I forgot to turn in my homework to the TA yesterday. Here is my homework." Now, as a teacher, I love to accept your homework, but in fact, when you do something like this, you're violating the class rule. No late homework assignment will be accepted. So what's going to happen? So now the principle of mine as a teacher is to help you accomplish the work on time. That's why I set up 2 important systems here. One is the traditional system, and you submit your homework to the TA on Wednesday so that the TA will have your homework to do the grading. And you submit the same standard homework on Tuesday through the Moodle environment so that I will have a record that you submit your homework. Okay? Now, what if you did not submit it to the TA, but you submitted electronically to me? Now, in case you became persons who fall into this kind of situations, the first thing you need to do is to write me an email and CC to the TA. Okay? That you did submit the homework electronically, but you forgot to turn in the homework to the TA in person during the Wednesday sections. Then, with your email received, I will pass the email to the TA and invite the TA to download the PDF copy of your submitted homework, and he or she will grade your homework, but not without penalty because you did not submit your homework on time. I will not tell you what the penalty is, but indeed you have to follow the rule. That is a very important principle of doing things on time. All right? So let me take off my clothes first. It's hot. Okay, having said that, I hope that you will not do something like this week. We do have some kind of practice that we would like you to stick to it. No homework assignment late, okay? And make sure you submit also the scanned copy of the homework through the Moodle environment on the same day. You submit the homework in person to the TA, and submit the returned graded homework through the Moodle environment on the next day, which is normally Thursday. So if you look at the websites today, for particular for this week, you can see that week number 5, we have submissions of the homework assignment number 3 on Wednesday, and submissions of the graded homework assignment number 2 on Thursday. All right? And for this particular week, you have 1 more submissions to make, which I'm going to add here. Remember what? It's the journal. It's the first time you have to submit the journal. Only 4 times we're going to collect the journal. What are the journals? Journals are the notes you take based on the number of sections we have finished from the beginning of the semester up to last week. So study the teacher's message of last week, which is week number 4. Here we go. You got the teacher's message of last week. There, I've given you a reminder. This week, on February the 4th, you need to submit homework number 3 with this number of sections, so many questions. You have a quiz number 2 to write on this Wednesday, and you also have the journal to submit, which includes the notes. Now, principally speaking, your notes should cover the following sections from the textbook, okay? And you could submit your notes as the scanned copy of your handwriting notes, or the best thing is you can also do in Microsoft Word notes, and you submit the Microsoft Word document, which is already given here. So make sure this is the first time we are going to collect the journal from you, and this is submitted through the your Moodle link. You can see the submission link by this evening, okay? So remember that. And let's go back to our class normally. So having done the 4 important weeks of study in Calculus 1, for those of you who have already been following very closely what we have been doing over the past 4 weeks, you should know that I have given you, at the end of each week, something called end of the week activity. If you look at the end of the week activity of last week, I have already repeated the teacher's message of last week as well as given you a very relatively completed resources for you to review what we have gone through so far, except for 2.7, 2.8, okay? So today we're going to go into implicit differentiations, which is also part of what your chapter 3 covers. And before we go to the exponential functions or the logarithm, but remember, okay, as far as the resources we've gone through, these 4 important lectures, you need to review it very carefully in order to understand what we have been going through, chapter 1, chapter 2, and chapter 3. And all of these problems suggest a problem you need to work it on your own with the solutions given, so you have a very good discussions here. And together with the recitations, that means the TA is going to give you working example based on this topic, just 10 minutes each, so it's a very important resource for you to review. We are about to finish the basic part on differentiations after this week, and we're getting on to integrations, okay, after the Chinese New Year's holiday, okay? So you have all the wonderful time after this week to enjoy the material we covered so far, using the time given to you of the Chinese New Year's framework, okay? So today, let's get started with the specific topic of implicit differentiations, okay? That is lecture number 5. So once you're ready, let's get started, which is a continuation of David Jerrison's work, which is very important, part of chapter 3.
Or to view additional materials and visit MIT courses. Visit MIT open courseware at ocw.mit.edu.
So we're ready to begin the fifth lecture. I'm glad to be back. Thank you for entertaining my colleague Haynes Miller. So today we're going to continue where he started. Namely, what he talked about was the chain rule, which is probably the most powerful technique for extending the kinds of functions that you can differentiate. Now we're going to use the chain rule in some rather clever algebraic ways today. So the topic for today is what's known as implicit differentiation. So implicit differentiation is a technique that allows you to differentiate a lot of functions.
functions. We do have a problem.
Functions you didn't even know how to find before. And it's a technique. Let's wait for a few people to sit down here.
We just did.
Physics, huh? Okay. More physics.
I hope that the lines are in this room today. You're not reading the system, I think it's not giving it wrong.
Powerful technique for extending the kinds of functions that you can differentiate. Now we're going to use the chain rule in some rather clever algebraic ways today.
The subtitle may not be available here directly from MIT, okay?
What's known as implicit differentiation.
Let's try.
We'll take a break. You can get those after class. All right. So we're talking about implicit differentiation, and I'm going to differentiate several examples.
They're competing now.
A lot of functions you didn't even know how to find. This is one of the most, and it's a technique.
Okay, here we go.
For a few people to sit down here. Physics, huh? Okay. More physics. We'll take a break. You can get those after class. All right. So we're talking about implicit differentiation, and I'm going to illustrate it by several examples. So this is one of the most important and basic formulas that we've already learned part way, namely the derivative of x to a power is a times x to the a minus 1. Now, what we've done so far, what we've got so far is the exponents 0, plus or minus 1, plus or minus 2, etc. You did the positive integer powers in the first lecture, and then yesterday, Professor Miller told you about the negative powers. So what we're going to do right now, today, is we're going to consider the exponents which are rational numbers, ratios of integers. So a is m over n, and n are integers. Right, so that's our goal for right now, and we're going to use this method of implicit differentiation. In particular, it's important to realize that this covers the case n equals 1, and those are the nth roots. So when we take the 1 over n power, we're going to cover that right now, along with many other examples. Okay? So this is our first example. So how do we get started? Well, we just write down a formula for the function. The function is y is equal to x to the power m over n. That's what we're trying to deal with. And now there's really only 2 steps. The first step is to take this equation to the nth power. So write it as y to the n is equal to x to the m. All right, so that's just the same equation rewritten. And now, what we're going to do is we're going to differentiate. So we're going to apply dy dx to the equation. Now, why is it that we can apply it to the second equation, not the first equation? So maybe I should call these equations 1 and equation 2. The point is that we can apply it to equation 2. Now, the reason is that we don't know how to differentiate x to the m over n. That's something we just don't know yet. But we do know how to differentiate integer powers. Those are the things that we took care of before. So now we're in shape to be able to do the differentiation. So I'm going to write it out explicitly over here without carrying it out just yet. That's d by dx of y to the n is equal to d by dx of x to the n power. And now you see expression here requires us to do something we couldn't do before yesterday. Namely, this y is a function of x. So we have to apply the chain rule here. So this is the same as, this is by the chain rule now, d by dy of y to the n times dy dx. And then on the right-hand side, we can just carry it out. We know the formula. It's m x to the n minus 1. All right, so this is our scheme. And now you'll see in a minute why we win with this. So first of all, there are two factors here. One of them is unknown. In fact, it's what we're looking for. But the other one is going to be a known quantity because we know how to differentiate y to the n with respect to y. That's the same formula, although the letter has been changed. And so this is the same as, I'll write it underneath here, n y to the n minus 1 dy dx is equal to n x to the n minus 1. Okay, now comes, if you like, the non-calculus part of the problem. Remember, the non-calculus part of the problem is always the messier part of the problem. So we want to figure out this formula. This formula, the answer over here, which maybe I'll put in a box now, has this expressed much more simply, only in terms of x. And what we have to do now is to solve for dy dx using algebra, and then solve in all the way in terms of x. So first of all, we solve for dy dx. So I do that by dividing the factor on the left-hand side. So I get here m x to the m minus 1 divided by n y to the n minus 1. And now I'm going to plug in. So I'll write this is m over n. This is x to the n minus 1. And now over here, I'm going to put in for y x to the m over n times n minus 1. Okay. So now we're almost done, but unfortunately we have this mess of exponents that we have to work out. I'm going to write it one more time. So I already recognize the factor a out front. That's not going to be a problem for me, and that's what I'm aiming for here. But now I have to encode all of these powers, so let's just write it out. It's m minus 1, and then it's minus the quantity n minus 1 times m over n. All right, so that's the law of exponents applied to this ratio here. And then we'll do the arithmetic maybe just over here in the next board. So we have here m minus 1 minus n minus 1 m over n is equal to m minus 1. And if I multiply n by this, I get minus m. And if the second factor is a minus minus, that's a plus. And it says plus m over n. So altogether, the two m's cancel. I have here minus 1 plus m over n. And lo and behold, that's the same thing as a minus 1. All right, so this equals a x to the a minus 1. Again, just a bunch of arithmetic. From this point forward, from this substitution on, it's just the arithmetic exponents. All right, so we've done our first example here, and I guess I want to give you a couple more examples, so let's just continue. The next example, I'll keep it relatively simple. So we have example 2, which is going to be the function x squared plus y squared is equal to 1. Well, that's not really a function. This, again, is a way of defining y as a function of x implicitly. There's the idea that I could solve for y if I wanted to. And indeed, let's do that. So if you solve for y here, what happens is you get y squared is equal to 1 minus x squared, and y is equal to plus or minus square root of 1 minus x squared. So this, if you like, is the implicit definition, and here is the explicit function y is a function of x. And now, just for my own convenience, I'm just going to take the positive branch, right? This is the function, just draw it right above here. Right? It's really a circle in disguise, and I'm just going to take the top part of the circle. So we'll take that top function. All right, so that means I'm erasing this minus sign. I'm just taking the positive branch. Just for my convenience, I could do it just as well with the negative branch. All right, so now I've taken the solution and I can differentiate this. So rather than using this dy by dx notation over here, I'm going to switch notations on over here because it's less writing. I'm going to write y prime and change notations. Okay, so I want to take the derivative of this. Well, this is a somewhat complicated function here. It's the square root of 1 minus x squared. And the right way always to look at functions like this is to rewrite them using the fractional power notation. All right? That's the first step in computing a derivative of a square root. And then the second step here is what? Somebody want to tell me? What? Chain rule. Yeah, that's good. Chain rule, that's it. So we have two things. We start with one, and then we do something else to it. So whenever we do two things to something, we need to apply the chain rule. So 1 minus x squared square root. All right, so how do we do that? Well, the first factor I claim is the derivative of this thing. So this is a half y to the minus 1/2. So I'm doing this by the sort of advanced method now because we've already graduated. We already did the chain rule last time. So what does this mean? This is an abbreviation for the derivative with respect to blah of blah to the 1/2, whatever it is. Right, so that's the first factor that we're going to use. Rather than actually write out a variable for it, and pass through, as I did previously with this y and x variable here, I'm just going to skip that step, and I'm going to let you imagine it as being a placeholder for that variable. So this variable is now parentheses. And then I have to multiply that by the rate of change of what's inside with respect to x, and that is going to be minus 2x. All right, the derivative of 1 minus x squared is minus 2x. And now, again, we're glomming everything together here. We couldn't have done this example 2 before example 1 because we needed to know that the power rule worked not just for a integer, but also for a equals 1/2. We're using the case a equals 1/2 right here. It's 1/2 times, and this minus 1/2 here is a minus 1. Right? So this is the case a equals 1/2, a minus 1 happens to be minus 1/2. Okay, so I'm putting all of those things together, and within a week you have to be doing this very automatically. So we're going to do it at this speed now. You want to do it even faster, ultimately. Yes? The question is, could I have done it implicitly without the square roots? And the answer is yes, that's what I'm about to do. Okay? So this is an illustration of what's called the explicit solution. So this guy is what's called explicit. And I want to contrast it with the method that we're going to now use today. So it involves a lot of complications. It involves the chain rule, and as we'll see, it can get messier and messier. And then there's the implicit method, which I claim is easier. All right? So let's see what happens if you do it implicitly. The implicit method involves, instead of writing the function in this relatively complicated way with the square root, it involves leaving it alone. Don't do anything to it. In this previous case, we were left with something which was complicated, say x to the 1/3 or x to the 1/2 or something complicated. Okay, we had to simplify it. We had an equation 1 which was more complicated. We simplified it and then differentiated it. And so that was the simpler case. Well, here, the simplest thing for us, the simplest equation for us to differentiate is the one we start.
The bandwidth today is not so good, so just bear with it for a couple of minutes. You see, when more and more people enter the room with the mobile devices, the bandwidth allocated is smaller and smaller. So you can, maybe you can switch off a little bit of your phone and see if the bandwidth could be resumed. That it's a big pie divided into a number of small pieces. And we can actually calculate the rate of change of the bandwidth later on.
Because squares are practically the easiest things after first powers or maybe 0 powers to differentiate. So we're leaving it alone. This is the simplest possible form for it, and now we're going to differentiate. So what happens? We get, so again, what's the method? Let me remind you. You're applying d by dx to the equation. So you have to differentiate the left side of the equation and differentiate the right side of the equation. So it's this. And what you get is 2x plus 2y prime is equal to what? 0. Derivative of 1 is 0. All right, so this is the chain rule again. I did it a different way. I'm trying to get you used to many different notations at once. Here. Well, really just two, just the prime notation and the dy dx notation. And this is what I get. All right? So now, all I have to do is solve for y prime. So that y prime, if I put the 2x on the other side, is minus 2x, and then divide by 2y, which is minus x over y. All right? So let's compare our solutions. I apologize, I'm going to have to erase something to do that. So let's compare our two solutions. I'm going to put this underneath and simplify it. So what was our solution over here? It was a half 1 minus x squared to the minus a half times minus 2x. That was what we got over here. And that is the same thing if I cancel the 2's and I change it back to looking like a square root. That's the same thing as minus x divided by square root of 1 minus x squared. All right, so this is the formula for the derivative when I do it the explicit way. And I'll just compare them, these two expressions here. And notice that they are the same. All right, they're the same because y is equal to square root of 1 minus x squared. Yeah, question?
Bottom half of the circle.
The question is, why did the implicit method not give the bottom half of the circle? Very good question. The answer to that is that it did. I just didn't mention it. Well, wait, I'll explain. So suppose I stuck in a minus sign here. Okay, I would have gotten this with a different, so with an extra minus sign. But then, when I compared it to what was over there, I would have had to have another different minus sign over here. So actually, both places would get an extra minus sign, and they would still coincide. So actually, the implicit method is a little better. It doesn't even notice the difference between the branches. It does the job both on both the top and bottom half. Another way of saying that is, if you're calculating the slopes here, so let's look at this picture. Here's a slope. Let's just take a look at a positive value of x and just check the signs to see what's happening. If you take a positive value of x over here, x is positive, the denominator is positive, the slope is negative. You can see that it's tilting down. All right? So it's okay. Now, on the bottom side, it's going to be tilting up. And similarly, what's happening up here is that both x and y are positive, and this x and this y are positive, and the slope is negative. On the other hand, on the bottom side, x is still positive, but y is negative, and it's tilting up because the denominator is negative, the numerator is positive, and it's minus sign because of the positive slope. So it matches perfectly in every category. So this is complicated, however, and it's easier just to keep track of one branch at a time, even in advanced math. Okay? So we only do it one branch at a time. Other questions?
Great. That's very good.
Okay, so now I want to give you a slightly more complicated example here. And indeed, some of the, so here's a little more complicated example. It's not going to be the most complicated example, but, you know, it'll be a little bit tricky. Okay? So this example, I'm going to give you a fourth order equation. So y to the fourth plus xy squared minus 2 is equal to 0. Right? Now, it just so happens that there's a trick to solving this equation. So actually, you can do both the explicit method and the non-explicit method. Okay? So the explicit method would say, okay, well, I want to solve for this. So I'm going to use the quadratic formula, but on y squared. This is quadratic in y squared, because there's a fourth power and the second power, and the first and the third powers are missing. So this is y squared is equal to minus x plus or minus the square root of x squared minus 4 times minus 2 divided by 2. Okay? So this x is the b, this minus 2 is the c, and a is equal to 1 in the quadratic formula. And so the formula for y is plus or minus the square root of minus x plus or minus the square root of x squared plus 8 divided by 2. All right? So now you can see this problem of branches. This happens actually in a lot of cases, coming up in an elaborate way. You have two choices for the sign here, you have two choices for the sign here. Conceivably, there are as many as 4 roots to this equation because it's a 4th degree equation. It's quite a mess. You should have to check each branch separately. And this really is that level of complexity. And in general, it's very difficult to figure out the formula for quartic equations. But fortunately, we're never going to use them. That is, we're never going to need those formulas. So the implicit method is far easier. So the implicit method just says, okay, I'll leave the equation in its simplest form and now differentiate. So when I differentiate, I get 4y cubed y prime plus, now here I have to apply the product rule. So I differentiate the x and the y squared separately. First, I differentiate with respect to x, so I get y squared. Then I differentiate with respect to the other factor, the y squared factor, and I get x times 2y, y prime. And then the 0 gives me 0, so minus 0 equals 0. All right, so there's the implicit differentiation step. And now, I just want to solve for y prime. So I'm going to factor out 4y cubed plus 2xy. That's the factor on y prime. And I'm going to put the y squared on the other side, minus y squared over here. And so the formula for y prime is minus y squared divided by 4y cubed plus 2xy. So that's the formula for the solution. for the slope. Do you have a question? So the question is, for the y, would we have to put in what we solved for in the explicit equation? And the answer is absolutely yes. That's exactly the point. So this is not a complete solution to a problem. We started with an implicit equation, we differentiated, and we got, in the end, also an implicit equation. It doesn't tell us what y is as a function of x. We have to go back to this formula to get the formula for x. So for example, well, let me give you an example here. So this is the hides a degree of complexity of the problem, but it's a degree of complexity that we must live with here. So for example, at x equals 1, you can see that y equals 1 solves. That happens to be solves y to the fourth plus xy squared minus 2 is equal to 0. That's why I picked the 2 actually. So it would be 1 plus 1 minus 2 equals 0. I just wanted to have a convenient solution there to pull out of my hat at this point. So I did that. And so we now know that when x equals 1, y equals 1, so at 1, 1 along the curve, the slope is equal to what? Well, I have to plug in here minus 1 squared divided by 4 times 1 cubed plus 2 times 1 times 1. That's just plugging in that formula over there, which turns out to be minus 1/6. All right, so I can get it. On the other hand, but at, say, x equals 2, we're stuck. Using this formula star to find a y. Okay? Now, so let me just make 2 points about this, which are just philosophical points for you right now. The first is, when I promised you at the beginning of this class that we were going to be able to differentiate any function you know, I meant it very literally. What I meant is, if you know the function, we'll be able to give a formula for the derivative. If you don't know how to find a function, you'll have a lot of trouble finding the derivative. So we didn't make any promises that if you can't find the function, you will be able to find the derivative by some magic. That will never happen. And however complex the function is, a root of a 4th degree polynomial can be a pretty complicated function of the coefficients. We're stuck with this degree of complexity in the problem. But the big advantage of this method, notice, is that although we had to find star, we had to find this formula star, and there are many other ways of doing these things numerically, by the way, which we'll learn later. So there's a good method for doing it numerically. Although we had to find star, we never had to differentiate it. We had a fast way of getting the slope. So we needed to know what x and y were, but y prime we got by an algebraic formula in terms of the values here. But this is very fast for getting the slope, once you know the point.
It takes time to practice them. That's right, the homeworks. Well, during this break, because we're still waiting for the bandwidth, those of you who have the textbook,
Yes.
okay.
what's in the parentheses, sorry. This is, well, let's see if I can manage. Is this little, is this the parentheses you're talking about? Ah, say. This is say. Well, so maybe I should put commas around it. But it was S-A-Y, comma, comma. Okay? Well, here was at x equals 1. And here's but at, say, I'm just throwing out a value here. Any other value. Actually, there is one value, my favorite value.
You love to problem different number to get the points across. In your textbook, your office would use something like a similar reasoning to help you understand different examples too. That's why during the break I was suggested, because of the bandwidth problem, you can look over the textbook, okay, with between sections 3.3 to 3.5, something like this, to look over the related materials on implicit differentiations. Now, interestingly, those of you who have the textbook, you can actually refer to the index to look up the keyword implicit differentiations and go back to the pages and look it back. Now, this is one way to check what you have been studying with what the textbook can provide. Now, if you have the textbook, go to the back pages called index and look up the keyword implicit differentiations and
well,
try to see.
Okay. Right? X equals 0. I can do it here. That's maybe the only one which is. The others are nuisance. Okay. All right. Other questions? Okay, now we have to do something more here. So I claimed to you that we could differentiate all the functions we know, but really we can learn a tremendous about some functions which are really hard to get at. So this implicit differentiation method has one very, very important application. To finding inverse functions, or finding derivatives of inverse functions. So let's talk about that next.
There we go, inverse functions, chapter 3.
So first, maybe we'll just illustrate by an example. If you have a function y is equal to square root of x, for x positive, then, of course, this idea is that we should simplify this equation and we should square it and get this somewhat simpler equation here. And then we have a notation for this. If we call f of x equals the square root of x, and g of y is equal to x, this is the reversal of this, then the formula for g of y is that it should be y squared. And in general, if we start with any of y is equal to f of x, and we just write down, this is the defining relation for a function g, the property that we're saying is that g of f of x has got to bring us back to x. And we write that in a couple of different ways. We call g the inverse of f, and also we call f the inverse of g. Although I'm going to be silent about which variable I want to use because people mix them up a little bit, as we'll be doing when we draw a few pictures of this. So let's draw a picture of both f and f inverse on the same graph. So first of all, I'm going to draw the graph of f of x is equal to square root of x. Right? That's some shape like this. And now, in order to understand what g of y is, so let's do the analysis in general, but then we'll draw it in this particular case. If you have g of y is equal to x, that's really just the same equation, right? This is the equation g of y is equal to x. That's y squared equals x. This is y equals square root of x. Those are the same equation. It's the same curve. But suppose now that we wanted to write down what g of x is. Okay, in other words, we wanted to switch the variables, so we'll draw them, as I said, on the same graph with the same x and the same y axes. Then that would be, in effect, trading the roles of x and y. We have to rename every point on the graph, which is the ordered pair x, y, and trade it for the opposite one. And when you exchange x and y, so to do this, exchange x and y. And when you do that, graphically, what that looks like is the following. Suppose you have a place here, and this is the x and this is the y. Then you want to trade them, so you want the y here, right, and the x up there. So it's this sort of opposite place over there. And that is the place which is directly opposite this point across the diagonal line x equals y. So you reflect across this, or you flip across that, and you get this other shape that looks like this. And I'll draw it with a colored piece of chalk here. Right? So this guy here is y equals f inverse of x. Right? And indeed, if you look at these graphs, this one is the square root. This one happens to be y equals x squared. Right? So if you take this one and you turn it, you reverse the roles of the x-axis and the y-axis. Tilt it on the side. All right, so that's a picture of what an inverse function is. And now I want to show you that the method of implicit differentiation allows us to compute the derivatives of inverse functions. So let me just say it in general, and then I'll carry it out in particular. So implicit differentiation allows us to find the derivative of any inverse function, provided we know the derivative of the function. All right? So let's do that for what is an example which is truly complicated and a little subtle here and has a very pretty answer. So we'll carry out an example here, which is the function y is equal to the inverse tangent. So again, for the inverse tangent, all of the things that we're going to do are going to be based on simplifying this equation by taking the tangent of both sides. So let me remind you, by the way, the inverse tangent is what's also known as arctangent. That's just another notation for the same thing. And the way what we're going to use to describe this function is the equation tan y is equal to x. That's what happens when we take the tangent of this function. So this is how we're going to figure out what the function looks like. All right, so first of all, I want to draw it, and then we'll do the computation. Okay? So let's make the diagram first, make the sketch. So I want to do something which is analogous to what I did over here with the square root function. So first of all, I remind you that the tangent function is defined between two values here, which are pi over 2 and minus pi over 2. And it starts out at minus infinity and curves up like this. So that's the function tan x. Okay? And so the one that we have to sketch is this one which we get by reflecting this across the axis, all right? So that's going to be, well, not the axis, sorry, the diagonal. Right? This slope, by the way, should be less, so a little lower here so that you can have it going down and up. All right, so let me show you what it looks like. So on the front end, it's going to look a lot like this one. So this one has curved down, and so the reflection across the diagonal curved up. Here, this is curving up, so the reflection is going to curve down. It's going to look like this. Right? Sorry, let's use a different color because it's reversed from what we had before. So I'll just call it blue. Right? Now, the original curve in the first quadrant eventually had an asymptote which was straight up. So this one is going to have an asymptote which is horizontal, and that level is what? What's the highest right there? It says pi over 2 up here. All right. Now similarly the other way, we're going to do this, and this bottom level is going to be minus pi over 2. So there's the picture of this function. It's defined for all x. So this green guy is y equals tan inverse x. And it's defined all the way from minus infinity to infinity. And to use a notation that we have from limit notation, as x goes to infinity, let's say, tan inverse x is equal to pi over 2. That's an example of one value that's of interest in addition to the finite values. Okay, so now the first ingredient that we're going to need is we're going to need the derivative of the tangent function. So I'm going to recall for you, and you maybe haven't worked this out yet, but I hope that many of you have, that if you take the derivative with respect to y of tan y, so this you do by the quotient rule. So this is of the form u over v, right? We use the quotient rule. So I'm going to skip this. Okay? But what you get in the end is some marvelous simplification. It comes out to be cosine squared y. 1 over cosine squared. You can recognize the cosine squared from the fact that you should get v squared in the denominator. And somehow the numerator all cancels and simplifies to 1. Okay? And this is also known as secant squared. All right? So that's something that If you haven't done it yet, you're going to have to do this as an exercise. Okay, so we need that ingredient, and now we're just going to differentiate our equation. And what do we get? We get, again, d by dy tan y times dy dx is equal to 1. Or, if you like, 1 over cosine squared y times, in the other notation, y prime is equal to 1. So I just used the formula. All right, now all I have to do is solve for y prime. It's cosine squared y. Okay? Unfortunately, this is not the form that we ever want to leave these things in. Again, this is the same problem we had with that ugly square root expression or with any of the others. We want to rewrite it in terms of x. Our original question was, what is d by dx of tan inverse of x? Now, so far, we have the following answer to that question. It's cosine squared of tan inverse x. Okay? Now, this is a correct answer, but way too complicated. Now, that doesn't mean that if you took a random collection of functions, you wouldn't end up with something this complicated. But these particular functions, these beautiful circular functions involved with trigonometry, all have very nice formulas associated with them. And this simplifies tremendously. And so one of the skills that you need to do to develop when you're dealing with trig functions is to simplify this. And so let's see now that expressions like this all simplify. So here we go. There's only one formula, one ingredient that we need to use to do this, and then we're going to draw a diagram. So the ingredient, again, is the original defining relationship that tan y is equal to x. So tan y equals x can be encoded in a right triangle in the following way. Here's the right triangle, and tan y means that y should be represented as an angle. And then its tangent is the ratio of this vertical to this horizontal side. So I'm just going to pick two values that work, namely x and 1. Those are the simplest ones. So I've encoded this equation in this picture. And now, all I have to do is figure out what the cosine of y is in this right triangle here. In order to do that, I need to figure out what the hypotenuse is. But that's just square root of 1 plus x squared. And now I can read off what the cosine of y is. So the cosine of y is 1 divided by the hypotenuse. So it's 1 over square root, whoops, yeah, 1 plus x squared. Okay? And so cosine squared is just 1 over 1 plus x squared. And so our answer over here, the preferred answer, which is way simpler than what I wrote up there, is that d by dx of tan inverse x is equal to 1 over 1 plus x squared. Okay? Now, maybe I'll stop here for one more question. I have one more calculation which I can do, even in less than a minute. So we have a whole minute for questions. Any questions? Yeah? Say that again? What happens to the inverse tangent? the inverse tangent is, okay, so this inverse tangent is the same as this y here. Those are the same thing. So what I did was I skipped this step here entirely. I never wrote that down, but the inverse tangent was that y. The issue was, what's a good formula for cosine y in terms of x? So I am evaluating that, but I'm doing it using the letter y. So in other words, what happened to the inverse tangent is that I called it y, which is what it's been all along. Okay, so now I'm going to do the case of the sine, the inverse sine. And I'll show you how easy this is if I don't fuss with, because this one has an easy trig identity associated with it. So if y is equal to sine inverse x, and sine y is equal to x, and now watch how simple it is when I do the differentiation. I just differentiate, I get cosine y times y prime is equal to 1. All right? And then y prime, so that implies that y prime is equal to 1 over cosine y. And now to rewrite that in terms of x, I have to just recognize that this is the same as this. Which is the same as 1 over square root 1 minus x squared. So all told, the derivative with respect to x of the arc sine function is 1 over square root of 1 minus x squared. And so these implicit differentiations are very convenient. However, I warn you that you do have to be careful about the range of applicability of these things. And you have to draw a picture like this one to make sure you know where this makes sense. In other words, you have to pick a branch of the sine function to work that out. And there's something like that on your problem set, and it's also discussed in the text. So we'll stop here.
So today
You have watched and learned the context of implicit differentiations, also the range of differentiations. What does it mean if you realize that there is something called implicit differentiations? Also, to the explanations here, there is something called explicit differentiations. Now, my questions to you is, after you have read and watched the demonstrations of the concept and technique here, with the continuations of the derivative sine and cosine functions in the past week, why we need implicit differentiations? Ask yourself this question. The answer is actually there already. Okay? Why do we need something called implicit differentiations? Now, if you flip over to chapter 3, okay, you see all the different sections here, but looks like you cannot find the term implicit differentiations label its heading of a particular section. What does it mean from the perspective of the author's point of view? Okay, now think a little bit more about this, and definitely you can look at related information on the chapter 3 concerning the same theme you discussed today. Okay, so study the textbook, and we will come back to have more discussions. And you visit the website today on week number 5, you will observe that I have not actually added in anything specific yet, which I'm going to add in today, including the readings. Okay, the reading for this week will be up and make a line by the end of this evening. And for the other particular readings of video as well as notes, I would invite you to make sure you visit all the links in week number 4 first, particularly the end week activities of last week. Okay? So you just have to remember what you have actually covered. And look at that, I come back to this again. I start off today's class by telling you, you should have already gone through all those sections here. Okay? And we are somewhere in applications of derivative. And again, find the derivative of trigonometric functions, the discussions of chain roots last week. And this week, we come to implicit differentiations. Well, that means what? If you cannot find the answers to my questions I gave you just now, come back to this link, okay? And study another very good tutorial provided by Professor Leona, all right? So this is what I would like you to do before we come to our first day's class. But definitely, I need to remind you one more time, this coming Wednesday, you have a quiz, which is based on sections 2.4, sections 3.1, and sections 3.2. Now, since we're going to cover 3 sections in this Wednesday's quiz, you can expect you have 3 questions to write, 10 minutes per question, okay, in this Wednesday's quiz. And you also have to submit the homework for this week, which is assignment number 3, right? And then you have to get back to return the homework grade for assignment number 2, and this is what you need to do. And for those of you who came in late, remember, if you happen to forget to submit your homework to TA, okay, but you have already done the submissions through the Moodle environment, make sure you write me an email, CC to the TA, just in case you will consider that you have missed the homework. Okay? Homework is meant to be an exercise, and do not want to miss it. But again, be punctual. Do not forget. This is one of the reasons for turning in your homework late. All right? So let me come to take attendance for today. The best thing about the coming Lunar New Year's is to have enough time to get ready for the second half of your course before the midterm exam, okay? And we're about to start integrations soon. Licky, are you here today? Thank you. Terry, thank you. Eden, thank you. Jason, thank you. Goodwin, thank you. And then Jan, thank you. Amy, thank you. Susie, thank you. Bob, thank you. Vivian, thank you. Song, thank you. Rachel, thank you. Luana, thank you. Sue, thank you. Pete, thank you. Elaine, thank you. Kent, thank you. Alphys, here. Okay. Anson, thank you. Okay. Caesar, thank you. Alex, thank you. Tina, thank you. And then Garjon, are you here? Not today. Sinhan, are you here? Sinhan, not here. Kian, thank you. Simon, are you here? Again, not here. Okay. William, thank you. Stain, thank you. Esther, she's excused today. Ita, thank you. May, thank you. Cora, thank you. Logo, thank you. Thank you, Logo. Jackie, thank you. Amber, thank you. Kay, thank you. Thank you very much. All right, I'll see you on the first day. Please get ready for the quiz this Wednesday. That's it for today's class, MATB 110, Section 1. After this first day, stay tuned.